Hello, and welcome back to another lesson with Alex from the Calculus Corner. Alright, so today we're going to be going over the alternate form of a derivative. Alright, let's get into it here. So, first thing that we can ask is, what is the alternate form of a derivative? So the alternate form is given by the equation that the derivative of f at the point c, f prime of c, equals the limit as x approaches c of the value f of x minus the value of f evaluated at c over x minus the value c. So not only does this tell us what the derivative is at the point c, it also tells us if it exists automatically, and also tells us the relationship between differentiability and continuity. Because as we know, the limit won't exist unless it is continuous at that point from the right and the left. So this shows that if this gives us a value, it is differentiable and continuous at that point, which is very helpful for numerous different ways. Alright, so let's go through an example of just computing the alternate form, or computing a derivative using the alternate form. So let's do this example here. So given f of x equals x squared plus 4. Let's find f prime of 3 using the alternate form of derivative we discussed just now. So let's go back to the equation. The equation is f prime of some number c, which let's apply it here, of f prime of some number 3 in this case, because that's the number we are trying to find, equals the limit as value x approaches that number 3 of f of x in this case, which is x squared plus 4, and then we subtract, which would be, so we're subtracting f of 3. So let's compute f of 3 right here. Right, f of 3 would be 3 squared plus 4, which equals 13. So we plug this 13 back into the top here. Clean up my lines a little bit. We plug that 13 in the top over here, and then on the bottom we use that value x minus whatever value c we're approaching, which is 3. Alright, so then if we do some simplifying here, we notice at the top, which this simplifies to x squared minus 9. So x squared minus 9 can be factored to x minus 3, x plus 3, and all over this x minus 3 we saw before, so we know that these two values here cancel out. So then we just get the limit as x approaches 3 of x plus 3. And so if we use or plug in this 3 from the limit, we get the value of 6. So we know that this derivative, f prime of 3, equals 6. And we also know that it is continuous at that point. Alright. So, there we go. Let's go over another little logistic piece, or a little something that we know now that we have this alternate form. So we know that the existence of a limit, or for a limit to exist, has to exist from the left and from the right. So we know that for a limit to exist, it has to exist from the left and the right. So applying this to this alternate form, we want to make sure that this limit, as x approaches c from the left, of that f of x minus f of c over x minus c equals this value of the limit of x approaches c from the right of that same f of x minus f of c over x minus c. So this will both get us the derivative at that value c and prove to us that we can use that alternate form since we know that the limit there exists. So therefore, let's do a little theorem here. So therefore, we can now prove let me fix up my handwriting here. We can prove that a derivative exists at c by showing its limits from the left and right exist. And that is a great tool. Alright, so let's go on to a quick example. Alright, so let's write this down here in blue. Okay, so say we have the function f of x equals absolute value of x minus 2. And then we want to use the one-sided limits to prove that f of 2 prime does not exist. So first of all, let's look at the graph here of x, of this function here, of the absolute value of x minus 2. So here will be 1, 2. So we know that this is where it intersects the x-axis. And the absolute value function gives us this v-shaped function here. And at this point, this is where we're evaluating the derivative. But as we can see here, it has like an instant change in its direction. So just based off pure intuition, we can see that we do not think that the derivative there will exist because of that sharp change in direction. So let's use these one-sided limits to prove that the derivative at that point does not exist. So let's recall this equation that we used for the alternate form of derivative. It would be the limit of f of x minus f of c over x minus c. So first, let's compute this from the left. Or first of all, actually, let's rewrite this absolute value function for clarity. Let's rewrite it as a piecewise function. So this x minus 2 absolute value can be split into, so you first, if you want to take it from the left, you take the negative of this, which would be negative x plus 2. And this is on the domain of x is less than or equal to 2. Because we can see here on this graph on the left again that the slope is negative on the left of that value of x of 2. And I'm just assigning this one to equal to 2 because you have to assign one of the points or one of the equations to have that equals 2. And then for the other side, you keep the original equation. So this is from the right. So it would be x minus 2 on the domain of x is greater than 2 because we can see here that the slope is positive going towards the right. So with these piecewise functions here, let's compute the limits from the left and the right. Let's go back down here. So the limit as x approaches c from the left in this case. So f of x from the left in this case is that negative x plus 2 minus f of c, so it would be f of 2 evaluated on that equation, which would be 0 over that original x, so x minus the value of c, which is 2. So we see here that we get negative x plus 2 over x minus 2, because this 0 doesn't mean anything. So this we can split as negative of x minus 2 over x minus 2, so we get negative 1 for this limit. So this is the limit from the left right here, negative 1. And if we take the limit from the right, 2 from the right, we use f of x again, but this time it's from the right, so we use this second of the piecewise functions, which is x minus 2. Plugging in 2 to this equation, we also get 0. And we do this over that same x value minus c, which is x minus 2. So here we get x minus 2 over x minus 2, which we know simplifies to 1. And so now we see, the limit from the left and the right are not equal. 1 does not equal negative 1, which proves to us that this limit, or this derivative at 2, does not exist. So that's the gist of it, and let's do one more example here. Because, let's go over quickly this. So in this case, the limit does not exist, because we can see on this graph, or the sort of graphing characteristic you can see that shows this limit does not exist is that sharp turn that we see on the graph here. Alright, so let's go over another one quickly. Alright, so let's take the equation. Let's take the equation f of x equals x to the 1/3. Okay, so let's go over the graph of this one again, because I want to relate the derivatives to what the graph looks like. The graph of this one looks like this. It'll go here, like that. Let me redo this actually. It's not a great sketch. There we go. That's a bit better. So we're evaluating, or we're looking for the derivative at the point f prime of 0, or at the point 0. So we were looking for f prime of 0 to see if it exists or not. So we're looking for that right here, and what the derivative would be right there. And so just looking at this graph now, we can see that this gives us almost a vertical line at that point if we take the tangent line to it, the tangent line being the slope at that point, which is what the derivative is. So let's prove that we don't think this exists since the slope is directly straight up. So we'll take the limit from the left of that alternate form, which is x to the 1/3 minus 0 over x minus 0, which we get to be 1 over x to the 2/3, or the limit of this. And so we see here that we get 1 over 0. So we know this limit does not exist. So already, we don't even need to take it from the other side, since one of the limits does not exist. So, since the limit does not exist, f prime of 0 does not exist. We can see that characteristic in the graph again. That vertical line for the tangent at that point. Alright, so let's just go over, let's review all of the general rules we came up with in this lesson. Just we have a sort of simplified way of thinking about things. We'll name this let's name this the conclusion. Alright, so first, let's see. So, in conclusion, the derivative does not does not, wow, I really am having trouble doing this right now, does not exist when there is some sort of, say, vertical asymptote. We didn't go over this in the lesson, but so if there is some vertical asymptote, so with something such as, let's see, if it were to be like this, we see this vertical asymptote here. So the derivative at that point, since the limit here is going to be different than the limit here, or the limit on this sort of line of x, these are not going to be equal limits, right? Okay. And because they don't exist, so that's another thing. So then the second thing would be what we saw in the last example with x to the 1/3 on this graph, how it went sort of vertical at its tangent. So it has a vertical tangent line. And the third would be where it is not continuous, which is what we see when the two limits, the limit from the left does not equal the limit from the right. Alright, and that's all I have for everyone today, and I hope everyone enjoyed the video, and I hope that it clarified some things about why this test is useful and why it is used. So thank you everyone very much, and I will see you again soon.